2.7 piecewise functions. Your essential question: how do you represent piecewise functions and use them to model real-life quantities? And to start this, I'm using a little example of overtime. So at your job, you earn $10 per hour weekly. If you work more than 40 hours within 1 week, you get paid time and a half, which means you get your original wage, that $10, plus 50% more. So 50% of $10 would be $5 more. So that means that after 40 hours, you're basically making $15 an hour. This is very typical for most hourly jobs out there. That's jobs that pay you an hourly wage instead of just saying, hey, you make this much per year. Okay, hourly wage means you make this much per hour. But if you go above and beyond that maximum full-time hours, which is 40 hours, you get time and a half. All right, so we have some questions to answer. How much money do you earn after working 50 hours? And what equation or equations represent your weekly pay no matter how many hours you work? And then we'll graph the equations. Notice I put a little S here because it actually ends up, piecewise functions actually end up being more than one equation. Okay, it's not something that's just always changing at the same rate. Sometimes things change at different rates. Okay, so let's explore this. So for number one, I'm going to make a table. So I'm going to start with the number of hours that I work. I'll call that N. And then I think I'll do another column that's the money that I make, or my salary. And I'll call that, how about S? Okay, so if I think about this, let's see. So I'll make a little table here. So if I work 1 hour, well, I've made $10. If I work 2 hours, I know I've made $20. So if I've made, and this is basically, right, this is 10 times 2. So for 2 hours. So if I've worked 40 hours, well, that's basically going to be 10 times 40, or $400. Okay. Now what happens when I work above that? So let's just kind of draw ourselves a little line right here. Because this is me working a full-time job, not doing any overtime. Once I go above 40 hours, now I'm getting paid overtime. So at 41 hours, well, I'm still making that $400 up to 40 hours. Plus now, time and a half, again, is at $10 plus half, which is $15 an hour. So I'd make $15 times 1, or in other words, I'd make $415. Okay, what if I work 42 hours? Still made that $400 from when I was just getting my regular pay, plus my overtime pay now for 2 hours. Well, that's $430. We'll do that one more time, see if we can recognize a pattern. So for 43 hours, I'm making $400 plus that $15 an hour times 3 hours. So it's going to be $445. All right, so let's see. So if I'm making, if I'm working 50 hours, well, I'm going to get my $400 of original pay plus my $15 per hour of everything that's over 40 hours, right? So 50 hours is 10 hours over. So that's going to be 400 plus 15 times 10, or $550 if I work 50 hours. All right, so let's try and figure out some equations to represent this. Well, I think the first equation, okay, so doing this part, this piece right here, just representing up to 40 hours, well, that one's pretty straightforward, right? It was 10, let's see, this was 10 times 1, 10 times 2, 10 times, basically it's 10 times the number of hours that I work. So this equation here, for just this piece, would be 10 times the number of hours that I work. That's going to be my income, or my salary. Okay, well, what about the rest of this? Okay, so this is becoming, I'm already making $400, right? no matter what, because I worked that 40 hours. But here I'm going to add to it for every hour over that 40 hours. So if I work 41 hours, this is 15 times 1, because this 1 comes from subtracting the 40 and the 41. So what you really end up with here, you end up with, no matter what, you get $400, plus you get 15 times the number of hours that you work that is above 40 hours. So for this section, you get you get 400, I got excited about that, 15. You get $400 no matter what, plus, now notice here, if I work 41 hours, that's 1 above 40. If I work 42 hours, that's 2 above 40. So it's going to be 15 times, and now I'm going to do n minus 40. Again, because I'm taking that n, I'm subtracting 40. That's how I'm getting that 1 right there. So I have two separate equations to represent two separate pieces here. Okay, so my function actually looks like this. There are two pieces. The first piece, actually, let me just set up the whole thing. S of n, salary as a function of number of hours that I've worked. There's going to be two parts to this, so I'm going to put this little bracket. The first part was just, hey, it's the number of hours that I work times the amount of money that I make. And that's going to be true when I work any number of hours between 0 and 40 hours. Now the second piece, and if I want to put my slope first, my slope here, the rate of change here is 15, right? Every time it's going up by another $15. You can see that here. Every time this is going up by 15. Every time this one here, this one's going up by 10, right? That's my slope. So I think I'll put my slope first, just to keep in the same format that we like to see. So we're going to say, all right, well, 15 times n minus 40 plus that initial $400 that I worked, those initial 40 hours earning. So this is going to be any time that I work more than 40 hours. That's a piecewise function. I've got two separate equations, each representing a different part of the domain. So the domain is what my inputs are, right? What my x values or my independent variable is. All right, so there's my equations. And think about it, does it work if I put in 50 here? Right, does that work? If I put in 50, well, that becomes 10 additional hours, makes it $150 additional dollars that I got paid, plus 400. And then the last part of this, we'll graph them. And I'm just going to do a pretty rough graph here. Let's see, what can I do? Because these are going to be pretty darn big numbers. So, how about we go? Well, the first graph is pretty simple. And this goes from 0 to 40. So these two equations are basically going to they're going to have different slopes at 40, right? The first piece will go all the way up to 40. The second piece, though, begins after 40. So 40 is kind of like your breaking point. I think of that as like, oh, the two pieces are kind of breaking apart. They basically have different rates of change. This one will have $15 per hour. This one will have $10 per hour. All right, so if I work 0 hours, I get 0 money. And then from there, I basically go up for every, I should label my axes. I haven't done that. So this is my salary. This is my number of hours worked. So we'll call this S. And we'll call this N. Sorry. I got a little excited. I didn't label my axes, but that's super important. Okay, so every time that I work an hour, I go up $10, right? So if I earn $10 for every hour I work. I earn $10 for every hour I work. And I can keep doing this, right? Until I get up at 40 hours, I'm going to be at $400. Okay, so I'm just going to roughly put, how about I put it up here? So at 40, I'm making, and it was a steady rate of change. So for every hour I work, I earn $10. Every single time I go up 10 over 1, up 10 over 1, up 10 over 1, okay, until we get to here. So my first piece of this graph, up to 40 hours, has this constant rate of change, $10 for every hour. But after that, well, what does my slope become? My slope actually becomes 15, right? So after that, my slope now, I make $15 for every hour. So now I'm like $15 for every hour. So basically I end up with a steeper rate of change. We're not going to go into too much detail just yet, but a graph of this might look something like this. Ooh, they would actually connect right there. Let's try that one more time. Just be a steeper rate of change. There we go. That might be too steep, but you get the idea. And we'll get to practice a bit more of this. Okay, so once again, this one's going to have a rate of change of 10 over 1. This one's going to have a rate of change of 15 over 1. So let's define a piecewise function. A piecewise function is a function represented by a combination of equations just like above. I'll talk about that in a second. Each corresponding to a part of the domain. Okay, so what do I mean by this? Well, this is an example. Number 2 here, we came up with our piecewise function, right? We've got one function that happens to have two separate equations, right? One of them, we can think of this, like for example, we can think of each one of these as separate equations. One of them is s equals 10n, and the other one is s equals 15 times n minus 40. Plus 400. Those are two separate equations. Now, each one of these equations relates to a certain part of the domain, a certain part of the independent variable. This one goes from 0 to 40. So if I work from 0 to 40 hours, I use this equation. The other one is if I work any more than 40 hours, I use this equation. Okay? That's a piecewise function. Example 1. Evaluate f of x for the given values, then graph f of x. So we have a piecewise function, and this is how they're going to be written. Okay, you have one function that is equal to two separate pieces, two separate equations here, each one with its own domain. So if I'm on the x-axis and I'm anywhere less than or equal to 3, I'm looking at this equation here. If I'm on the x-axis and I'm looking at anything greater than 3, I'm going to use this equation here. Looking at A, it says when x equals 3. So which of these domains includes where x equals 3? That's correct, the first one, which means that when I'm evaluating this function at x equals 3, I need to use the first piece of the function. So f of 3 will be 3 times, and that's where I plug 3 in, plus 2. So that's 6 plus 2, that's 8. I lied. That's 9 plus 2, so that's 11. For the second piece, for B, it's saying x equals 6. So again, the first place I need to go to is the domain. Which of these includes x equals 6? Well, this one where x is greater than 3, that includes x equals 6. So I'm going to use the second piece. So f of 6 will be equal to the second piece evaluated when x equals 6. So that's 6 minus 1, so that's 5. Okay, so we finished the first part, we evaluated. Now we have to actually graph f of x. So again, we're looking at our domain to determine where our graphs are going to be. Okay, so this thing breaks apart when x equals 3. So at x equals 3 on my x-axis, okay, at x equals 3, I'm going to have my function basically has two pieces. So I'm going to have my equations are not going to necessarily be connected. I will probably have two separate pieces or two separate lines. And that brings a good point. Can piecewise functions only be used with linear graphs? No. They can be used with any kind of graph, any kind of function. So we could use these with parabolas. We can use them with absolute value. We can use them with exponents. We can use them with any type of function that you learn. Okay. So my first piece is pretty simple. I'm just going to graph this like I would any other time. So I think of this as y equals mx plus b. So this is y equals mx plus b, right? Well, in this equation, this is my y-intercept. This is my slope. So this one's going to be very easy to graph. So y-intercept is 2, so I go up 2, put a dot. That's my first point. And then from there I use my slope to get my next point. So up 3 over 1. So my graph will be these two lines connected, or these two dots connected. So my graph looks like this. Problem is, what's it going to be at 3? Okay, so that's pretty important here. At 3, I need to know what it's going to be because that's where this first piece is going to stop. Okay, so at f of 3, thank goodness we already evaluated it. Well, it's 11. So let's see, this is 1, 2, 3. There's 11 up here. So at 3, I know that my output's 11. And because it says that x is less than or equal to 3, that means that I can actually have a value at 3 for this function. So it can be on this line. So I can go as long as I want, or as far as I want, anytime before 3, because everything that is to the left of 3 is included in the domain of this piece. But I can't go past 3. Okay, I can't go this direction on the x-axis for this piece. I need my next piece. So my second piece has a function of y equals x minus 1. Okay, so my second one is y equals x minus 1. So you may be saying, well, Ms. Frisk, this is going to be really easy. I know the y-intercept. I know my slope. Well, that's all great, but here's the problem. This second piece is when x is greater than 3. So I can't graph any of it before x equals 3. I have to do it all after. Okay, I'm going to show you one way, and then I'm going to show you another way. So there's a couple ways to go about doing this. So the first thing to do is to figure out, well, what is it actually at 3? Not that I can graph it there, but I can have a hole there that just kind of holds its place. Okay, so probably the best way of doing this is to start out with a table of values. So let's figure out at 3, what is this piece? Well, that's going to be 2, right? Plug 3 in, you get 2. So I know at 3, my output is actually 2. And I'm going to put a hole there because, again, well, first of all, this is a function, so it has to pass the vertical line test. So if I have a dot here and a dot here, it's not going to pass that vertical line test. It's not going to be a function. So that's a big deal. The second thing is that, right after 3, this function starts. So here's 3, but right after 3 is like 3.00000000001. Okay, and I need to include that in that function. So I need to include everything just right after 3. Okay, so that's why I put this hole here, because it can't be a solid dot, because the second piece is not where x equals 3, it's x greater than 3. Now from that point, I can use my slope to get another point. So I can just go up 1 over 1. I also already evaluated, so when x equals 6, I know that my output's going to be 5. And now this piece is everything that is greater than 3. So this goes on forever where x is greater than 3, right? X on the x-axis being greater than 3. This piece goes on like that. So there's my piecewise function. Okay, so I said I'd show you another way. This way involves a lot of erasing. So if you have good erasers, you can do that. So another way that I could have graphed this piece was I could have gone to, hey, I know how to graph this equation, y equals x minus 1. So I would go ahead and I would plot, this is my y-intercept, there's my slope. So I could plot my y-intercept real lightly and then use my slope to get a few points, right? So that would be my equation. So I could then graph this line. I'm doing it very lightly because I don't want to mess up my beautiful equation, my beautiful piece. And then once I had that line, I could say, well, I need it to be after 3. So I'd come back in and I'd erase everything, making sure that I kept that hole at 3. Because again, you need this to be a function, and if you have 2 outputs when x is 3, then you don't have a function. What you have is a problem in Algebra 2. Moving on to example 2, graphing a step function. So this is a type of piecewise function. Here I have 3 pieces, and each piece has its own domain. I'm going to ask you to please change the first domain. It should read from -4 to -3. So we would say that x is greater than or equal to -4 and less than -3. Okay? Now, each piece of this function just has a constant. So these are what we call constant functions. And basically that just means that g of x equals 1 if I'm in between -4 and -3. So what is the graph g of x equals 1? That's a good question. What does that look like? Or in other words, what does y equal 1 look like? Hopefully by now you realize that that is a horizontal line. It goes through y equals 1. All right, so I have 3 pieces here. One of them is going to be y equals 1. One of them is going to be y equals 2. And one of them is going to be y equals 3 in between these x values. Okay, so I'm going to go ahead and draw these graphs. So y equals 1 is the graph at y equals 1. It's a horizontal line. And I can only draw this horizontal line, though, between -4 and -3. So let me label my axes. Okay, so at -4, my graph y equals 1 starts. And now x can actually equal -4, right? It can be greater than or equal to -4. So at -4 on the x-axis, I'm going to start my y equals 1 graph, and I'm going to have a solid dot there. Now this graph goes all the way to -3. But notice at -3 it's not equal to. So I should not have a solid dot at -3. I should have an open dot. Okay? That open dot tells me that, well, it gets really, really close to -3, but it's not at -3. Okay? And that allows us to now do our second piece, y equals 2. From -3 to -2, noticing that x is greater than or equal to -3, which means I will have a closed dot at x equals 3. So let's see, so -3, sorry. So I'm going to have a closed dot at x equals -3, and then that goes all the way to +2, or sorry, to -2, not +2. So again, I'm keeping with the fact that this is a function, right? I don't have two closed dots on top of each other because that would tell me that, well, if -3 has two outputs, it is not a function. This open dot means it gets really close to -3, so it's like -3.00000000001 and so on. Okay, that's included on this graph, but -3 is not. -3 is actually up here. These types of graphs are used a lot when you talk about like parking rates at parking garages. If you've ever been to a big city, right? And this is a bad example because it's got negative numbers, so I won't talk anymore about that right now. All right, so let's do the last piece here. Y equals 3. If x is greater than or equal to -2 or less than -1. Okay, so again, y equals 3 is just that horizontal graph. And it's going to go from when x is equal to -2 and bigger than it all the way to -1. So you end up with this step function. Example 3. A city parking lot uses the following rules to calculate parking fees. A flat rate of $5 for any amount of time up to and including the first 3 hours. So this is talking about the domain, right? Up to and including the first 3 hours. So that's telling me that my hours here are somewhere between 0 hours and 3 hours. Now, would it make sense for me to actually include 0 in a parking garage? Does anybody go to a parking garage and park for 0 hours? No. So I probably shouldn't have that equal to. Let's see if I can get rid of that. Okay. Second part is a flat rate of $12.50 for any amount of time over 3 hours and up to 6 hours. So here, I'm greater than 3 hours and up to 6 hours. So greater than 3 hours, but I could be equal to 6 hours, right? Because it's up to 6 hours. And then a flat rate of $13 plus $3 for each hour after 6 hours. So for this last piece, my domain then is anything greater than 6 hours. Okay, so that's going to be useful while we're graphing this. We're going to create a graph and a function rule, or just a function, to show the relationship between the amount of time you park your car and the total cost you pay for parking. All right, so I think I'll graph it first. So what I want to do is I'm going to have my x-axis, or my horizontal axis, be my hours. I know we're going, right here we're referencing, well, 3 hours, 6 hours, so anything greater than 6 hours. I don't know if I'm going to label every single hour here. But I'll go 0, 1, 2, 3, 4, 5, 6, maybe a couple after 6, okay? And then my cost from there, that's going to be my output, right? Because the amount of money that you pay at a parking garage is totally dependent on how long you park there. So this is going to be my cost in dollars. So let's see, if I'm talking about a flat rate of $13 plus $3 for each hour after 6, right? So that tells me that I've got $13 plus 3 plus, so maybe I'm somewhere like 16. Let's see how far up this will go. I think I'll go all the way up to $18. All right, so let's graph each piece of these. Okay, so the first one is a flat rate of $5, period, from 0 to 3. Okay, and again, you don't park in a parking garage for 0 time. Okay, you got to be there for some amount of time. So a flat rate of $5 at 0 time, I'm going to leave it open dot. And it's $5 as long as I park there just up to 3 hours. Okay, so that's my first piece. Second piece, a flat rate of $12.50 for any amount of time over 3 hours up to 6 hours. Okay, so $12.50. So again, at at 3 hours, I'm already paying $5. So after, like at basically if I stay 1 second after 3 hours, my rate jumps up to $12.50. I'm going to go halfway here. But I'll have an open dot there because again at 3 hours I'm paying $5. So I can't pay $5 and $12.50. And then this goes all the way up to 6 hours total. So at 6 hours I'm still paying $12.50. But then what happens at 6 hours, if I go over 6 hours by even a second, I'm going to get charged $13 plus $3 for every single hour after that 6 hours. So at hour 6, I'm still paying the $12.50. But as soon as 6 hours is up, now I'm jumping up to $13. And then it's going to actually jump up and continue on $3 an hour after 6 hours, right? So I'm going to jump up to $3 an hour. So let's see. Go up 1, 2, 3 for 1 more hour. And that would continue on 1, 2, but I'm off my graph now. So this is going to be basically a rate of change of $3 an hour. Let's see. So this one has a slope of 3, so I can go ahead and draw a line, and it's just going to continue on. All right, so let's come up with a function for all of these things. So we'll call this, how about C of H, because my cost is a function of my hours. So I'll make my function C of H. I'm going to have 3 pieces to my function, and I find it easiest to work with my domain first. So I think we already talked about that, right? I'm going to have one piece that talks about this domain, second piece that talks about this domain, and a third piece that talks about this domain. So my 3 domains will be, I'm going to go ahead and write them down. That way I can put what it equals next to it. Let's see, H being between 6 and 3, and then anytime H is greater than 6. So I feel like the first 2 pieces are really easy, right? What is this equation? This is just y equals 5. So that's just C of H equals 5. So it's going to be 5 for this first domain. Okay, how about our second domain? Well, the second domain, again, that's pretty easy. What is this equation? This is just y equals $12.50. So I can just put 1250 here. Okay, so the next one's going to be a little bit more tricky because notice this is not a horizontal line. There's a slope here. There's a y-intercept, which I don't actually know the y-intercept, but I do have a point that's on this equation, or that's on this line, and I do have the slope. So what if I used point-slope form to come up with that equation? Because I have a point and I know the slope. So the slope I have is 3, right? I rise $3 per extra hour. And the point that I came up with by using that was 16. So I'm going to go ahead and this is 7/16, right? So that point right there is at 7 hours, I pay $16. Okay, so I'm going to use the point 7/16. So this is going to be my x1, this is going to be my y1. All right, so y minus 16 equals 3 times x minus 7. And now the problem is I have to get this into y equals something, right? And then I'll put that over here. And I'll use h instead of x as my input. So let's see, we got y minus 16 equals 3x minus 21. Add 16 to both sides. Minus 5. And so I'll just call this, instead of having this an x, my input here happens to be hours, so I'll use h. So this piece of my function is 3h minus 5. And that's only when hours are greater than 6. Okay? Going on to example 4. Kind of a similar type of problem. So now we've been given the piecewise function as a graph, and we have to actually write the function. Okay? So you can call this function y, or maybe we should call it f of x so that we have it in function notation. So f of x has a few pieces, right? Again, it has 3 pieces. They can have, 20 pieces. But this one happens to have 3, the one before happened to have 3, the one before that happened to have 3. So we're kind of just, for whatever reason, those are the ones that we have. All right, so the first thing, I like to write down my domains first for each piece, and then go back and identify, okay, what is that exact function? So my first piece here looks like it's anywhere where x is less than or equal to negative 3. So my first piece is going to be where x is less than or equal to negative 3. My second piece, and again, I'm just looking straight on the x-axis. Okay, I'm looking, what is my domain of these pieces? And the domain is all your inputs, or the x-axis. So looking at this piece of the function, my domain seems to go from negative 3 to 0. But notice how these are both open dots. So there will be no equal to at all. Okay, so for that one, x is going to be in between negative 3 and 0. Okay, and then the last piece here seems like it goes from 0 forever on, right? It goes forever, the x-axis just keeps getting bigger and bigger and bigger, and I'm sure that there's outputs over here somewhere. So this is going to be anywhere where x is greater than, or it's a solid dot, equal to 0. Notice, again, we want this to be a function, so it can't be equal to 0 here and equal to 0 here. You only get one of them. Can't be equal to negative 3 here and equal to negative 3 here. You only get one of them. All right, so now I have to come up with the equations of the functions. All right, so starting with this one, y equals negative 2, right? So that's f of x equals negative 2. That's my first piece. Second piece, this one happens to have a y-intercept. So for this one, I can actually use slope-intercept form to come up with the equation of this line. So what's my slope? It looks to me like I'm going down 1 over 1. So it seems to have a negative slope. I'll just put negative x instead of negative 1. And it also has my y-intercept. Gosh, could this have gotten any better for us? My y-intercept is positive 4. So this equation then goes here for this piece. Negative x plus 4, that piece is equal to f of x in this domain. And the last piece. The last piece goes from here up to there. Again, we have a y-intercept, and we also have a slope. So there's no reason why I can't use slope-intercept form here to come up with that piece of that equation of that piece. So my slope, again, seems to be up 1 over 1. So y equals x, and my y-intercept is 0. So this is really just y equals x. So I'll put f of x equals x when x is greater than or equal to 0.